Hey everyone, ready to dive into some seriously mind-bending stuff?
Always.
Today we're exploring the world of experimental quantum technology.
The kind of stuff that could revolutionize, well, pretty much everything.
Exactly. We'll be guided by a fascinating essay by Yorigo Schneeppet.
It's called Innovationen in der experimentellen Quantentechnologie.
Catchy, right?
In it, Schneeppet gives us a deep dive into this cutting-edge field.
He covers everything from quantum cryptography to computing and sensing.
He really highlights those practical applications, too.
But before we get ahead of ourselves, Schneeppet starts with some history and theory.
Gotta have that foundation, right?
Absolutely. So let's unpack some of these weird and wonderful quantum mechanics concepts that Schneeppet lays out.
Sounds good to me.
Okay, so first up we have superposition,
Yeah, superposition. Think of it like a coin.
a coin.
Yeah, but it can be both heads and tails at the same time.
Whoa, that's trippy.
That's kind of what's going on with those quantum particles, too.
They're in this fuzzy state of multiple possibilities.
Until we try to measure them, that is.
So they're like, make up your mind, particle.
Pretty much.
But this fuzziness, how did that even work in technology?
Well, that's what makes quantum computers so powerful.
Ah, I see. Because they're not limited to just one state.
Exactly. They can explore all those possibilities at once.
Way faster than our everyday computers.
Exponentially faster, in fact, for certain problems.
So it's like a computer trying every solution at the same time.
You got it. A total game changer.
Okay, what other mind-bending concepts does Schneeppet throw at us?
Well, get ready for entanglement.
Entanglement.
This one is even weirder.
Uh-oh. Weirder than a coin being both heads and tails.
Way weird. Okay, imagine two of those coins, right?
Okay, 2 coins.
Both heads and tails at the same time.
Still with me?
Yet separate them, like really far apart.
Across the room.
More like galaxies apart.
Whoa, okay.
Now you flip one coin.
Okay, flipping.
The other coin instantly flips to the opposite side,
No way.
no matter how far apart they are.
That's insane.
That's entanglement, spooky action at a distance.
Okay, I officially have chills. But this isn't just theoretical, right?
Nope. Schneeppet talks about how it's applied in cryptography.
So like secret codes and stuff.
Exactly. Entanglement is the key to something called QKD,
2KD.
quantum key distribution. It makes encryption theoretically unbreakable.
Unbreakable. How?
Well, if someone tries to eavesdrop on an entangled communication,
Yeah.
the entanglement breaks down.
So they get caught.
Instantly. It's like a built-in alarm system for your messages.
That's seriously cool. But I think it's time for a little history lesson.
Agreed.
Schneeppet walks us through how we got here. How did we even start talking about entangled particles and these unbreakable codes?
Right. It wasn't an overnight thing. Schneeppet traces it back to the early 20th century.
So like over 100 years ago?
Yep. Guys like Max Planck, Albert Einstein, and Niels
The
Bohr.
big names, huh?
They were wrestling with some fundamental questions about, well, everything.
Like the nature of light and matter.
Exactly. Their theories laid the groundwork for what we now know as quantum mechanics.
It's amazing to think those ideas came from so long ago. But I'm guessing the path wasn't exactly straight.
Oh, not at all. Schneeppet stresses that scientific progress is a team sport.
Makes sense. One giant puzzle, everyone adding a piece.
You got it. And
Yeah.
sometimes it takes decades for those pieces to fit together.
Speaking of puzzle pieces, let's talk experiments. Schneeppet highlights some key ones, right?
He does.
Like, I remember the double slit experiment from, like, forever ago.
Mm,
Blew my mind.
it's a classic.
You shine light through 2 tiny slits. What do you think happens on the screen behind it?
Two bright spots?
Nope. It's an interference pattern, like light and dark bands.
As if the light's acting like a wave.
Exactly. Spreading out, overlapping with itself.
Super weird.
Wait, it gets weirder. Schneeppet says they even fired single electrons through those slits.
Electrons, those tiny particles.
Yep. And they still got the same interference pattern.
As if each electron went through both slits at once.
It's like they're messing with us.
Superposition in action. Until we measure it, it's going through both.
So they finally choose a slit when we look.
You got it.
Mind-blowing.
The double slit experiment really shook up how we see the world.
I can imagine. It's not just particles or waves. It's
Both. It all depends on how we observe them.
this wave-particle duality. Schneeppet calls it a cornerstone of quantum mechanics, right?
Right. And it all started with a simple experiment.
Pretty amazing. But Schneeppet doesn't stop there. He brings up another wild concept. Non-locality.
Ah, yes. Non-locality. Buckle up. Things are about to get even spookier.
Okay, lay it on me. Spookier than tiny particles being two places at once.
Imagine those entangled particles again.
The coin thing.
Yep. They can influence each other instantly, no matter how far apart they are.
But wouldn't that break the laws of physics? Like, how can they talk across such distances?
That's the beauty of quantum mechanics. It often defies our expectations.
Hmm.
And Schneeppert points out that this isn't just some wild theory. He brings up Bell's theorem. It's a mathematical framework for testing non-locality. Experiments have shown that Bell's theorem is violated, meaning non-locality is real.
No way. So things really can be connected, like, across the universe.
It seems so.
Schneeppert really drives home that this spookiness isn't just some cool fact. It's the very basis for all those groundbreaking technologies we talked about earlier.
You're catching on. Now that we've dipped our toes into the basics, let's dive headfirst into those applications.
Quantum computing, cryptography, sensing,
Schneeppert breaks down how these mind-bending concepts are being used right now.
and how they might reshape our future. I'm hooked. Lead the way.
Coming right up! Welcome back. It's amazing to think those principles, like superposition and entanglement.
The stuff we were just talking about.
Exactly. They're not just theoretical, like brain teasers.
Right.
They're being used to create real technologies.
Jorgo Schneeppert, in his essay Innovationen in der experimentellen Quantentechnologie.
He takes us through some of the most exciting applications in the field.
One that really caught my eye was quantum simulation.
Oh yeah, quantum simulation. It's basically using quantum computers to model complex systems.
Complex systems, like what kind of systems are we talking about?
Anything, really. Molecules, materials, financial markets, even the climate.
So instead of doing those time-consuming, expensive experiments in a lab,
You could run a simulation on a quantum computer.
and get insights that would be impossible otherwise.
Exactly. Schneeppert gives this great example of how it could revolutionize drug discovery.
Drug discovery.
Imagine being able to simulate how a drug molecule interacts with a protein, like at the atomic level.
Wow.
You could test thousands of candidates virtually
That would speed up drug development tremendously.
and potentially lead to cures for diseases we can't treat now.
That's incredible. It's like having a fast-forward button for science. But how do these simulations even work?
Well, remember those crazy principles of superposition and entanglement?
Of course, the coin thing, right?
Exactly. Quantum computers use qubits, which can be in multiple states at once.
Right. They hold all those possibilities simultaneously.
That's what gives them the edge over classical computers for these complex problems.
Makes sense. But Schneeppert also mentions that building these quantum computers is a massive challenge.
Whoa, absolutely. It's not easy.
He talks about different approaches, like ion traps, superconducting qubits, and photonic systems.
It's like a quantum buffet of technology. But to be fair, each has its own pros and cons, right?
Definitely. So break it down for us. What are these different approaches?
Well, let's start with ion traps. They use electromagnetic fields to trap ions. Those become your qubits.
Okay, ions are the qubits.
They're great because they have long coherence times.
Coherence times, that's like how long the qubits can stay in character before they mess up the calculations.
That's a great way to put it. Then you have superconducting qubits.
Okay, what are those?
Think tiny electrical circuits that act like artificial atoms.
Artificial atoms.
Yeah.
That's wild.
Super fast, can be controlled with microwaves. Good for those complex computations.
Sounds impressive. What about photonic systems? Schneeppert mentioned those too.
Ah, yes. Photonic systems use photons, those particles of light, as qubits.
Photons, like from light bulbs.
The very same. One big plus is that they can work at room temperature.
Oh, that's handy. Some of the other types need super cold environments, right?
Exactly. So it's like a toolbox, different tools for different quantum jobs.
And Schneeppert makes it clear that it's still early days in this field.
Yeah.
Scientists are constantly experimenting with new stuff to build better quantum computers.
It's a rapidly evolving field, full of potential.
But still, tons of challenges before we have quantum computers sitting on our desks.
Oh yeah, definitely. Lots of work to be done.
Speaking of exciting applications, Schneeppert also delves into quantum cryptography. We talked about QKD earlier.
Right, quantum key distribution. Super interesting stuff.
Can we go a little deeper? How does it work?
Well, it uses the principles of quantum mechanics to create, like, super secure encryption keys.
Super secure how?
If someone tries to snoop, to eavesdrop on a QKD-protected message, they'd leave a trace, They'd be detected instantly.
It's like a self-destructing message if anyone tries to peek, right?
That's a good way to think about it.
Hmm.
And Schneppat also discusses the concept of a quantum internet, which is super futuristic.
A quantum internet, what would that even be like?
It's a global network, but instead of our regular internet protocols,
Yeah.
it would use quantum principles for transferring information.
So not just secure communication.
It could revolutionize all sorts of things. Distributed quantum computing,
Hmm.
new types of sensing, incredibly precise measurement.
Sounds mind-blowing, but also incredibly hard to build, right?
Oh, absolutely. We'd need huge advancements in quantum communication.
Schneppat mentioned quantum repeaters, right?
Yeah, we'd need those to extend the range of quantum signals.
Without messing up those delicate quantum states.
That's the tricky part.
Okay, let's talk about the big one. Quantum computing.
The elephant in the room, right?
Schneppat dedicates a big chunk of his essay to this, and it's clear why.
It's a potential game changer.
Quantum computers could revolutionize so many fields.
Medicine, material, science, AI, cybersecurity.
It's like a Swiss Army knife of computation.
Hmm.
But Schneppat doesn't just hype it up, he also talks about the challenges.
Absolutely. It's not a magic bullet, at least not yet.
One thing I remember reading about was quantum supremacy.
Ah, yes, a big milestone.
Google claimed to have achieved it a while back. What does it even mean?
It means a quantum computer performed a task that's practically impossible for a classical computer.
Like, way faster.
Way, way faster. Think a calculation that would take a classical computer thousands of years.
Yeah?
The quantum computer did it in minutes.
Wow. Does that mean we're close to having quantum computers in our homes?
Hold on, not so fast. Schneppat points out that quantum supremacy is just one step.
Okay, what else is there?
Well, there's scalability. Building a quantum computer with a few qubits is one thing,
Right.
but we'd need hundreds or thousands for real-world problems.
Makes sense. And those quantum systems are also very fragile, right?
Yeah, error correction is another big hurdle.
Protecting those delicate qubits.
Exactly. We need to make these computers more robust and fault-tolerant.
Sounds like a lot of work ahead.
It is, but the progress so far is super exciting.
Definitely. But Schneppat also digs into the ethical implications of all this. He doesn't just focus on the tech itself.
He takes a broader view, which is important. With any powerful technology, we need to consider the why and the what if.
It brings up some big questions, right?
Oh, absolutely. Like, who will have access to these tools? Will everyone benefit?
Right, and how do we make sure this technology is used responsibly?
He's calling for a thoughtful, proactive approach. We need to shape the future of quantum tech, not just let it run wild.
So it's not just about the science, it's about the impact on society as well.
Exactly. It needs to be a conversation involving everyone, not just scientists.
It's wild to think how far we've come from these abstract theories.
To real, working machines harnessing quantum mechanics.
Yorgo Schneppat, in his essay, Innovation in their Experimental in Quantum Technology.
He really nails the excitement of this field.
And the possibilities, too. One thing that stood out was the potential link between quantum technology and AI.
Ah, yes. Quantum and AI. A powerful combo. We already talked about how quantum algorithms could, like, supercharge machine learning.
Right. But Schneppat hints at something even bigger, right?
He suggests that quantum computers could lead to entirely new forms of AI.
New forms. Like, beyond just faster processing.
Exactly. Systems that learn and adapt in ways we haven't even imagined.
So we're not just talking about AI that can crunch numbers faster.
We're talking about AI that could be genuinely creative, intuitive.
Even emotionally intelligent.
It's a mind-blowing idea. It raises all sorts of questions about consciousness and the future as how we interact with machines.
It's like science fiction is becoming science fact. Schneppat really makes you think about the long-term impacts of all this, how these technologies might reshape our world.
He urges us to look beyond those immediate applications, to consider the broader societal and philosophical implications.
One thing he emphasizes is the importance of collaboration.
Right. Schneppat points out that progress in quantum technology has been a global effort.
Scientists all over the world working together, building on each other's ideas.
And he argues that this spirit of collaboration is crucial as we move forward, especially with those ethical and societal challenges that come with these powerful technologies.
So it's not just about the science. It's about how we use it. Who gets access? What are the risks? How do we ensure responsible development?
It's a conversation that needs to involve everyone, not just scientists, ethicists, policymakers, the public. We all have a stake in this.
Absolutely. Well said. Schneppat's essay has given us a lot to ponder. from those fundamental principles of quantum mechanics to those awe-inspiring applications that could reshape our world.
It's a powerful reminder that we live in an extraordinary time, a time of incredible scientific advancements.
And it's up to us to engage in these conversations, to ask the tough questions, to work together to ensure that these quantum leaps lead us to a brighter future.
Well said.
Thanks for joining us on this deep dive into the world of experimental quantum technology. We hope you enjoyed exploring these mind-bending concepts and revolutionary applications with us.
Keep those minds open to the wonders of the quantum world.
Until next time, stay curious.